Okay, welcome to the class Complex Analysis. Okay, uh, for this class, we use this textbook, the John Conway, sorry, not John Way, John Conway's Functions of One Complex Variables, especially second edition. So the textbook. The textbook is John Conway's Functions of One Complex Variable. And second edition. Second edition. Okay, for this textbook, you can find this electronic version online, so you don't have to really buy a book. But if you like, this is a classical book. It is worth to own one copy. And here, let's see. In the table of contents, the first chapter is the complex number system, and second chapter is the metric spaces and the topology of complex numbers C. So these two chapters are fundamental. They are very useful in some places, but these two chapters are not the main part of the complex analysis. They are the pre-required material. So if we need any theorems or results from these two chapters, we will come back to them, but we will not discuss these two chapters in detail. Okay, so we will start the class from the third chapter. We will directly start from the third chapter, elementary property and examples of analytic functions. All right? Okay. So I'm going to say the chapter 1 and 2 are skipped. We'll start from the chapter 3. And during the whole semester, I plan to give a midterm exam and the final exam. The midterm exam these two exams will focus on the textbook. I will see if you understand the basic tricks or the basic results, and all the problems will come from either directly textbook or the exercise after textbook, which I assigned. So if I did not assign some problem to you, then they will not come to the exam. Okay, so the midterm and the final exam are the review, not review, like the refresh of the class. It's not a challenge, it's a class exam. Okay, and yeah, and that's it. So we are going to midterm exam is about the midtime, like after 2 months, not 2 months, 1 month and a half, we will have the midterm exam. The final exam will be during the final exam week. So that's a time schedule. I will let you know the detailed date in advance, and it is possibly on Friday from 5 p.m. to 7:30 p.m. It would be on Friday, some Friday, 5 p.m. to 7:30 p.m. We will see which Friday is good for the exams. Okay. Okay, very good. So that's a textbook and the exam. Now let's try to start the class, the chapter 3. The chapter 3 is elementary properties. And examples. Of analytic functions. Here is my email address. In any case you have questions about the class, just send me email. I'm happy to answer it. We can either talk through the Google Meet, or we can chat through the email, whatever way you like. Okay, so send me email if you have questions. Okay, now let's start. Okay, so chapter 3, elementary properties and examples of analytic functions, section 1, power series. Power series. So when we say power series, it is the following, the well-known stuff even from the calculus. So let an be in the complex planes for every n greater than or equal to 0. So including 0, we studied, it doesn't matter if n starts from what integer. But here we say n starts from 0 because later this power series will be like the polynomial, infinite polynomial. 0 means 0th order polynomial. It's a constant term. Okay, so that's why we when we study power series, n starts from 0. When we study a general series, n starts from 1, the first term. The first term has degree 0. Okay, then we will say that the series an converges to a point z in C if and only if this follows, if and only if. In the textbook they use IFF, if and only if. When you see IFF, it means if and only if. If and only if for every epsilon greater than 0, there is an integer capital N such that the absolute value of n from 0 to m a sub n minus z is less than epsilon whenever m is greater than or equal to capital N. This is an epsilon capital N language about the limit. Here, this is a partial sum from the 0th degree to mth degree. Okay? 0th degree to mth degree. This is a standard definition, convergence. And we say an, so sometimes we ignore the 0 infinity. We just write this symbol. Sigma an means n from 0 to infinity. An converges absolutely if the series absolute value of an converges. Okay, so the absolute convergence of a series just means you put ops value then the new series converges. That's the definition. All right? So you have first definition and second definition. But these two definitions are standard notations. Okay, standard definitions. You learn both in the calculus. Okay, so we also have the well-known fact. That's our proposition 1.1. If sigma an converges absolutely, then sigma an converges. Okay, so if you already know the series converges absolutely, remember that absolute convergence means another series converges. So it basically it says if this series with ops value converges, then the series without ops value converges. Okay? Okay, so how do we prove this? This is actually a very good application of a Cauchy sequence. Let's see the proof. So let epsilon be greater than 0 and define z sub n to be a0 plus a1 plus a sub n. So the partial sum of first n plus 1 terms, the partial sum of the first n plus 1 terms. Okay? And okay, so that's a definition. Now let's see. We know that a series an converges absolutely. In other words, we know that series ops value of an converges. This is exactly the meaning of absolute convergence. Okay, so we know this. Then there's what? There is an integer which is there is an integer capital N such that what? Such that the series n from capital N to infinity ops value of an is less than epsilon. So how do we get this stuff? How do we get this? It actually comes from the definition of a convergence of a series ops value of an. You know that here this one converges. Then for the same epsilon, there exists an capital N such that whenever m greater than or equal to capital N, the sum, finite sum an minus z minus some number is going to be less than epsilon, right? It's going to be less than epsilon. So that's a definition of absolute convergence. In other words, the tail will be short. You see, this z will be written as from 0 to infinity. Then this difference will be the sigma an n from m to infinity. This difference is like this. Well, there's might be a shift of this is m plus 1. This is m plus 1. So you kind of just cut the tail. The tail will be less than epsilon. So that's how they get it. Well, you can manage it to make this like a capital N. All right, so that's why in a textbook they directly give you this. So a positive series converges if and only if the tail can be controlled. This is the tail. Okay, here this is not part of the proof. This is a explanation why we have such stuff. Okay. Okay, then we know this. This is a whole discussion behind this symbol. Then, so if m and both greater than or equal to capital N, then we have, now we back to the original series. This is new series. This is original series. Zn minus Zm. Zn minus Zm. What is that? This is a partial sum of the first n plus 1 terms. This is partial sum of first m plus 1 terms. We see the difference. The difference will be the, let's assume they use k. Yeah, let's change a letter. Let's change a letter. And m greater than k. Let's change a letter. So n from k plus 1 to m, and then we have a sub n. You just get the difference between the k plus 1 terms and m plus 1 terms. And then we use a triangle inequality. Here is a triangle inequality, and then you let m approach infinity. And this one, we're going to use this conclusion is less than epsilon. Okay? Okay, so what we get? We get this, the sequence of the partial sum, or the partial sum sequence, is a Cauchy sequence. Right? For every epsilon, you can find a capital N such that when m and k greater than or equal to capital N, zk minus zm is less than epsilon. This is exactly the definition of a Cauchy sequence. And we know C is complete. It's complete. Complete means that every Cauchy sequence converges. Hence, this zk converges to z. Zk converges to z. It just means the sigma an converges. Okay, so that's the end of the proof, right? Okay, so this is the proof of absolute convergence imply convergence, right? And next, we know that not every sequence has a limit. Not every sequence has a limit. So whenever you want to study a sequence convergence or not, you have to prove something and verify some conditions. But in the following, we're going to introduce two different limits. They always exist, okay? So, okay. Let an be a sequence in R. This is a real sequence, not a complex. This is a complex sequence. This is a real sequence. We define the lim inf of an. The lim inf of an. Okay, so here, first, let's see the definition. The limit n approaches infinity. Okay, and then we're going to see the following. The infimum of an, an plus 1, an plus 2, and so on. So what is the idea? So you see here, the infimum an plus 1, an plus 2. So you just ignore the first n terms. Ignore the first n term, you compute the infimum. Every time when n approaches infinity, every time you ignore more terms. You ignore terms, the infimum does not decrease. The infimum is always increase. So basically here, we know the inf of an plus 1, an plus 2 is increasing, monotone, at least that's monotone, non-decreasing. So this limit, when I say this limit, means this right limit, this limit always exists. Always exists what? Always exists including infinity, negative infinity. Okay, it could be negative infinity. C, R union negative infinity. It could be negative infinity, so be careful, because infinity is in negative infinity, always negative infinity. Then that's a case. Okay, so by using the infimum about the term an plus 1, an plus 2, and so on, this you change a general sequence to a monotone sequence, then you can discuss a limit always. So this definition, because you use limit infimum, so it's called lim inf. And then you can study the corresponding one called lim sup an. Approaches infinity, the supremum of an plus 1, of course an plus 2. And here we know the supremum an plus 1, an plus 2, and so on is, you see, it's every time you skip term, supremum is decreasing, non-increasing. It's decreasing. So it's again, it's a monotone. So these two, you can both call them monotone. Monotonic. So this limit, again, always exists in R and union positive infinity. It could be positive infinity. Whenever you say supremum, it could be positive infinity. And sometimes, in some different textbook, you can have this notation. Upper bar. The upper bar is lim supremum, upper bound supremum, and the lim lower bar is a lim infimum. So that's a different notation. Inferior, superior. So limit lim inferior. It's a limit superior. Am I right? Yes. Limit inferior and limit superior. Okay. Okay, so that's the basic stuff. So we have the convergence, absolute convergence, implied convergence, and the lim inf and the lim sup definition. here let's add plus or minus. It's increasing could approach zero. Approach positive infinity. If it's always negative infinity, it's a negative infinity. So here's also plus or minus infinity. It's a decreasing. It may decrease to negative infinity. Okay, now let's see a power series. A power series about a number, a complex number A, is an infinite series of the form what? Of the form sigma n from 0 to infinity and a sub n and z minus a to nth power. So this is a so-called power series. This A is actually called the center of the power series. A is called the center of the power series. A sub n is the coefficient of the corresponding degree, nth degree. Right? Okay, so one of the simplest and most useful example is a geometric series. One is a series n from 0 to infinity, z to nth power. So in this example, a is 0, an is 1. An is always 1, a is always 0. So that's our geometric series. Geometric series. And we all know that in the series study, we know one is a arithmetic series, the other one is a geometric series, right? And because this let's use k from 0 to n, z to k's power is 1 minus z to k plus 1 over 1 minus z. We have such formula, right? So if absolute value of z is less than 1, then z to k's power will converge to 0 as k approaches infinity. The geometric series converges to what? Converges to 1 over 1 minus z. This term disappears. So you only have 1 in the numerator. Okay? And if it's greater than 1, then this limit, this one will blow out, right? This will approach infinity. Actually, the absolute value will approach infinity as k approaches infinity. So the geometric series diverges. The geometric series diverges, right? And the one z is absolute value of z is equal to 0. Well, there are two cases. Z is equal to 1, and not 0, 1. When absolute value of z is equal to 1, there are two cases. Either z is equal to 1. Z is equal to 1, this series diverges. Right? It is just infinity. If z is negative 1, you will have plus minus 1. It also diverges. It does not converge to any place. It does not even go to infinity. It's like jumping between, see what it is. It's 1 minus 1 plus 1 minus 1. So it's a 0, 1, 0, 1, 0, 1. It's between 0 and 1, jumping forever. So it diverges. Okay, so from this whole discussion, three cases discussion, we know that the geometric series makes sense if and only if the ops value of z's are less than 1. The geometric series makes sense if and only if this ops value of z is less than 1. So from this example, we also know that the power series, sometimes it will converge, sometimes it does not converge, right? In this one, this whole argument is based on this very powerful summation formula. But in general, we don't have such formula for the general power series, but we do have this theorem. Theorem says for a given power series, sigma n from 0 to infinity, a n z minus a to nth power, define the number r. Here this r could be between 0 and the infinity. It can be 0, it can be infinity. By 1 over r is equal to the lim sup of nth root of ops value of a n. Be careful, this n is a complex number. It's not just a real number. It can be whatever complex number, okay? So ops value means modulus of complex number. So you get ops value of a n and then take nth root and compute the lim sup. Then we have the conclusion 1, if z minus a is less than r, this is 1 over r, reciprocal of r. If it's less than r, the series converges absolutely. Absolutely. And if z minus a is greater than r, the terms of the series become unbounded. And so the series diverges. Okay, so why we say the terms becomes unbounded? One of the necessary conditions for a convergent series is that the limit of the term will approach 0, will be 0. Okay, but here it's unbounded, so it definitely the series. So you see here, it's different. The original series diverges. Here means series absolutely converges. It's actually stronger than convergence. Here is the conclusion about the series itself. Of course, series diverges. It will never absolutely converges. C. If we have any smaller number possible, if we possibly have any smaller number, for example, if r is 0, then this little r does not exist. So if 0 less than little r less than capital R, then the series converges uniformly on this closed disk centered at Well, let's put a little question mark here. It's not correct. Well, we will see why it's not correct. But in general, it says it's a uniformly convergence. It has a strong conclusion. But this is not correct. This should be z minus a, not z itself. Z minus a. Okay. Moreover, the number capital R is the only number having property A and B. Of course, from these two conditions, you can see it's definitely unique. It's a clear boundary. It's a clear boundary. It's this number R is like this 1. It's like this 1. It's 1 over 1, so R is still equal to 1. Inside, good. Outside, bad. So it's like the boundary. Okay. Well, let's see the proof. Let's see why we got such stuff. So here we assume that A is equal to 0. Well, A is like the center. You can shift this series from 0 to A, or you can shift the series from A to 0. So it does not bother the convergence stuff. So that's why we always assume A is equal to 0, but A could be any other numbers. And this is the reason why in the condition part C, the author put ops value of Z. It should be ops value of Z minus A. Z minus A. Okay. So to simplify the writing, you have A equal to 0. If you don't put here whatever rest of the computation, you just replace Z by Z minus A. Okay. You will see. Okay. If ops value of Z is less than capital R. So for example, here, if you don't do this writing, you will put Z minus A. Okay. So if you don't have such an assumption, you just always put Z minus A less than R. Whatever place you see ops value of Z, you will write ops value of Z minus A if you don't have such assumption. Okay. Ops value of Z is less than R, then there is, for a single point, this Z is selected and fixed. For a single point, there is a little r with ops value of Z is less than R, less than little r, a capital R, less than little r, less than capital R. Any two real numbers, there's a third number. Any two real numbers, there's a third number. Okay? Then there is an integer capital N such that the ops value of A sub n to the power n over 1 over n is going to be less than 1 over r. Little r is less than capital R, so 1 over r is greater than 1 over capital R. It's greater than 1 over capital R. And this is the lim sup. This is the lim sup. It's an increasing sequence. It's a decreasing sequence. Lim sup is decreasing. Lim inf is increasing. So, and it's an upper bound. So that technically, you have such a situation. You have such case for all n greater than or equal to capital N. We can always have such a thing. Okay? It will be used here. And this will imply, from here it will imply, so ops value of A sub n is less than 1 over r to nth power. 1 over r to nth power. And an z to nth power ops value, again, without this, it will be like this. It does not change anything. This one will be less than z over r. Oh, ops value. I put it here. Ops value z over r to nth power. Z over r to nth power. All right? This one is dominated by 1 over r. Z is z to n. For all n greater than or equal to capital N. Okay, so what is this? This tells us that this ANZN is dominated by this for n greater than or equal to capital N. So one series is dominated by the other series. One series is dominated by the other series. And we know that ops value of z over r is less than 1. Ops value of z over r is less than 1. So this series converges absolutely. Converges absolutely. Because this is a geometric series, it's bounded by it's less than 1. Again, remember, we select the z we fixed in this discussion. This z does not represent arbitrary complex number. It's just a single complex number. So this is a series of numbers, not a power series anymore. It's a series of numbers. Okay, power series usually that z represent is a variable. Now it's not a variable. So this converges absolutely, and a sub nz to n converges absolutely. Right? So it's the comparison test, the direct comparison test. So for whatever z with ops value less than r, you can always go through such thing. And this is the reason you use the definition 1 over capital R as a lim sup of it. And you see, that's why you have a reciprocal, because with the reciprocal, you flip it to the denominator, and you can control this z. All right, so this is a proof of part A. And let's see the part B. Part B, no, part B. Let's show the absolute uniform convergence. Part C now. So now let R less than capital R. R is less than capital R, and again, you have two real numbers. There's a third number between them. There is an row such that row is between little r and the capital R. And then there is a capital N such that, remember here the capital N with the property, with this property, a sub n to n to the power 1 over n is less than r. Less than r is less than 1 over rho. So less than where, here. Okay, so we have this, and for all where am I? Oh, for all n greater than capital N, the same thing. And if upper value of z is less than or equal to r, here again remember that if we do not assume a is 0, then this place is z minus a. Upper value of z minus a is less than r. That's why I say in the statement of C you have to write z minus a, because in the statement we don't assume a is equal to 0, but in the proof we assume a equal to 0 to simplify the writing. Okay, so if upper value of z is less than or equal to r, then we get what? Then a sub n z to n is going to be less than or equal to r over rho to nth power. R over rho to nth power. Okay, and now this time this n only depend on the value r and the rho. It does not depend on z anymore. It does not depend on z anymore. Here. So the convergence is uniform. So the convergence is uniform. It is uniformly convergence. Okay, so that's the difference between the previous stuff and this stuff. In the previous stuff, you need the z over r. Z over r, it depends on z. But here we have r over rho. It only r and the rho. It does not depend on the z. All right. Okay. Okay. So that's a part of C. Part of C, we got the uniform convergence. When you slightly shrink the disk a little bit. Now let's see the part B. Part B, we're going to show it diverges. Why part B it diverges? So let upper value of z is greater than r. Upper value of z is greater than r. And again, in two numbers, there's a third number between them. Choose r with upper value of z is greater than r, greater than capital R. And then we get 1 over little r is less than 1 over capital R. And this implies that there are infinitely many integers little n with the property that fails the condition. Usually we say the condition is where is it? It's more or less like this. Upper value of an is less than 1 over r to n, 1 over r. But here, because it's less than 1 over capital R, here this one should be greater than 1 over capital R. This part, we use a condition. One over rho is greater than 1 over capital R, then you have the same thing. But here is less than 1 over capital R, then it's not the limit of the supremum, then you can always find an integer. It breaks the condition. So it's b. It will be ops value of a sub n to the power 1 of n will be greater than 1 of r. And this implies that the a sub n z to nth power is greater than ops value of z over r to nth power. But this one is greater than 1. And it's not just greater than 1, and this ratio is greater than 1. If the ratio is greater than 1, you take nth power, it will be unbounded. These terms are unbounded. Right? It's not bounded, but we know that sequence limit exists if then not limit the series exists, then the limit of the term will be 0. The series exists, then the limit of the term will be 0. Actually, this is just a necessary condition, not sufficient condition, right? It's just a necessary condition. But here, even the necessary condition is not satisfied, so the series diverges. The series diverges. Okay? Okay, very good. So we prove the part B, 1 z minus a, it has ops value greater than r, then this power series diverges. Power series itself diverges. All right? Okay, thank you. We will stop the video at this point and continue the lecture in another short video. Okay, thank you. Just keep watching.